Okay, today I want to show how to parse some of the TLV structures in the game Monster Hunter Online. To do that, um, we first need to identify a structure we want to parse. So I actually have looked into back item. When I looked into back item, I realized it's actually the same structure as the equips item structure. So those are identical, back item, equip item. And then for the purpose of testing, I did the pet structure a little bit. However, that video it did not have the quality to actually see what's going on. So let me look into another structure from the player state that we want to look into. So let's try to use the skill structure, for example. So how can we figure out this skill structure? So the first thing I will do is I will say, okay, structure, skill, let's just say get skill. So I will make a new method for getting the skill data. To do that, I will copy paste this template here I had. Just call it get skill. Okay, so don't need all this. So all I really need is at the moment is the setup here, the placeholder, my case, and at the very end writing the size. So what's happening is first we're writing a header if we want to use variants or not. So I will use no variants. I think that should be easier. And then after that we are writing a placeholder of 4 bytes, which needs to be the size, but at this point in time we don't know the size yet. Then we're trying to write our data, and then we're setting our position back to here, and we write the actual size that we can know based on our position of the buffer. So what we need to do is, the first thing is I will write some data here. I just write a byte here, and write a tag, and we'll pass this structure to here. And now I run the server. So now I've basically give a basic structure to the data I want to look into. The next thing, I will start the game. I'll attach my debugger. So I already have a lot of breakpoints and annotations, and I've started to write them down here. I'll share that later. So now that our server is running, we are populating our structure. We need to somehow trigger the code that will give us the packet data. We can trigger this by selecting a character, because we know the character in the data will be sent whenever I select the character. The other thing we need to do is we somehow need to know how can we figure out which of all these codes is actually responsible for parsing the TLV structure. Let me disable some of my breakpoints here. So how can we find out what's parsing our TLV structure? We know that there is a method that reads a variable int, which should be the beginning of every parsing TLV structure. So I will copy this one. In my debugger, I press Ctrl and G to go to this offset. Okay. You can already see I gave it a name. This method is called readValueInt. You can give it a name if you mark the code like this. You press right click, you can say analysis, and then it has this called add function. And then you can press on the first instruction, and you press shift and colon, and then you can give this offset a name, which I have done here. So once you jump to this code, you would want to set a breakpoint here, that the execution stops whenever this code is run. So what we're going to do now is that when I press login, we're hitting this breakpoint because now it's actually trying to read, the function is trying to read this tag here. Right? So we made a tag with ID 0 and a type of 1 byte, and we write that. If you have multiple structures here enabled, like equip item and pet item, then they, of course, will also trigger the TLV parsing logic and will also go to this method call. So either you need to make sure that no other TLV structures are sent to isolate this one you're looking for, or you need to inspect if this is actually the ID you're looking for. So now if we're looking at the call stack, we see this method here called this one. Okay, so at this point in time it tries to read the var uint. So we know this whole method here, from here till the very end, probably here. Let me check. Could actually be a bit longer. I'm not sure. Yeah, I think it goes. Oops. Yeah, it goes to here, most likely, because I know these are the error codes. So I press analysis, add function. So now I have identified this function. I press shift colon, and I will say sub TLV skill. Yeah. So this is the function that passes the skill, because I know I've only sent a single TLV structure for the get skill, and it's being accessed here in the valueInt call. Where we set our breakpoint. Okay, so don't need this at the moment anymore. Then I want to most likely set a breakpoint at the jump table. This is a jump table. But for now, I want to be at the end of the readVar method. I'll get out of it, I come here. So what's happening now is this test, it actually tests if whatever I've read is valid, like test if read was successful. So I can add comments by pressing the semicolon key. Okay, and then we can see EAX000, which is no error. If we have an error, those are the error codes that are possible. Right now for this valueInt read, we don't have an error, so we don't jump out of it. So what happens next is I'm moving my read value, the value that has been read here, into a register. So I add another comment, move read value from memory to EDX register. Okay, So now if I go right click on here, I say follow and dump, I press on this one, I see okay, it has 0, 1 here. So why is it 0, 1? Is because this one actually is a composite value of two values. So the value we wrote is actually a value that has been combined with two values, the ID and the type. So right now the type is this one, which is actually a 1. And the ID was 0. So we actually have written tag had a value of 1 in this case. That's why we're seeing a 1 here. What this logic is doing here, it's actually extracting the ID, because this one is actually a ID plus type composite value, and it's been moved to EAX. Okay. What we then do is we shift this one by the 1 by 4 to the right. We're extracting the ID again. Extract ID. It will be in EAX after that. So after we perform this operation on the 1, we get our 0 back. Because our ID was 0, yeah, so we get our 0 back that we wrote here. And then what's happening next is it decreases EAX by 1. So it's basically same minus 1. So now we see our EX is FFFFF. So we're now checking if our value is, we're comparing our value against a 9. And then we say, okay, if our value is above 9, we jump. So if ID is, let's say if ID, only if ID is smaller or equals to 9, then okay, let's jump to exit. Okay, so we want to have an ID that is actually smaller or equal to 9, and we can see that our extracted ID is also subtracted by 1. So that means our range for the first ID in this scenario would be 1. So we want to adjust for that. So I want to say my ID is 1 because it will have ID 1 always minus 1 equals 0. So for our first case, we need to specify an ID of 1 to make it happen. Okay, and because now our ID is out of this range, we are jumping to the exit. So now that I have adjusted my ID to 1, I press apply my changes. I will put the breakpoint here as well, and I will just let it run now. Because I need to test it again now with the other value. So once I'm into the game, I need to trigger the packet again. So I just go back to my character selection, and I'll press login again. Bam. So now again, we're trying to pass the updated structure now. So now our EX is actually 0 instead of FFF. Why? Because the value we read here is, you can see it's 11. And then 11 has been shifted right by 4, which gives us the 0. So basically 11 is a compound value of the 1 ID and the 1 of the TLV type. Okay, so now that we have extracted our correct ID, we pass the check because 0 is not above 9. And now we are at the jump table. So this jump table, for each ID, it will execute different codes. Right now our ID is 0. So in this case, that would be case 0. Just call it case 0. So if our EXO would be so this breakpoint, I remove it. So if our breakpoint now would be, let's say EX is 1, so I change it to 1, you can see our jump arrow is adjusted to here. So now we know, okay, this is case 1. And then let's say our EX is then the ID is 2. Then our case go here. So we can say, okay, this one is case 2. And so on, right? So what's happening here is that we make a tag, we write it to the buffer, and here the tag is being read, the ID is extracted, subtracted by -1, and then a sanity check, and then based on the result, it will jump to a specific section of code. Okay. So what we can do now is we can press the G key for a graphical overview. It will help a little bit to visualize the different branches. So this one is the jump table here. If we go all the way to the left, we can see this one is the case 0 code. This one is case 1 code. One is case 2 code, and so on. If we're looking at case 1, we actually see that it calls the read integer method. So that means we actually want to write an integer here, not a byte. So we say write int. Let's just copy this one. Okay. So let's just write the integer, and we say this is AA. We want to adjust our tag type to be 4 byte. So the tag type should specify, I think, the size of this value, because it's an integer 4 byte, we want 4 byte. But I don't think the client code will actually check the tag. So in most cases, any tag should be fine, but just for consistency, I think it would be nice if that lines up. Okay. And then we can also construct our next case. Okay. So now, for case 1, what do we want? We want it to be ID number 2, because 2 minus 1 equals 1. So our EX register will be 1 at that point and jump to another point. So now again, I press my G key. I select the jump table, press the G key, and go to the left. I look at case 1. And what do I see? Oh, it's a bit complicated, this one. It says read a short. So this one may be a bit complicated, so I prefer, for case 1, we will be here. And we actually, we read a short. We test if the read was successful. If not, we are jumping out. If it's successful, we jump here and check if there's more data. Okay, so for case 1, we read the short. So in this case, write in 16. Let's say our value for this one must be B. I like to use something that's recognizable. Our tag has been adjusted. Our type wants to be adjusted for 2 bytes now. Okay. And then let's also make the next case, which is case 1, 2. So the ID needs to be incremented by 1, right? ID 3 minus 1 equals 2. For this one, for case number, for this case, for case 2, what's happening is this will be run, this will be run. We'll read an integer, and then it will actually try to read another integer. It will call an unknown method. Okay, so this one looks a bit more complicated. Yeah, so this one, case 2 is definitely more complicated. So what's happening here is we read the integer, we test if it was successful read, if not we jump out, then we do another test, probably is a bounds test because it looks like a substructure of some sort. So if I want to know what's this method. Oh, okay, so if we go to this method, we actually can see that it reads another var uint. So it reads a tag. So that means this one is a substructure. Okay? And this int is the size of substructure. And this one is size of all substructures. I know this because yeah, I've done this before, but basically what's happening is I will first tell it what's the total size, and then for each individual substrate we'll also have a size prefix, then it will write a structure. We can see that it has a GB here, not this one, jump lower. Okay, so basically we tell it the size of all substructures, it will do sanity checking, it will read the substructure size, it will read the substructure, and then it will compare it against the value 5. So it will check whether there is I have a maximum of 5 substructures. If it's lower than 5, or the jump equal means if I've reached the end of data. JA would be an error. This one is if, I think it should be an error. Let's see, where does it go? It goes to error FFDE. Yeah. So this one is an error. It means that if read is not the same as what we told is there, then it's an error. And this one is if we have actually reached the x equal, if we have read equals what we told you to read, then it's okay. So in case we only have 2 structures, 2 substructures, and one substructure is 10 bytes long, we can say, okay, you have 20 bytes of substructure data. And if I have exactly 20 bytes read, then I know, okay, I'm done. You told me I have 20 bytes, I've read 20 bytes, I've done, even though I've only read 2 substructures. So whatever happens first, either if I've read the exact number of bytes you've told me to read, I'm done, or if I have read 5 substructures, then I'm also done. If I've done neither of those, I will jump because I'm lower, and I will read the next structure. Okay, so what we know for case number 3 is we need to write 2 integers. Okay, so first let's say, okay, this one is definitely a 4 byte, and it will be integer 23. So this one is the size of all substructs, and then size of substructure. Okay, and I've done this before, so it's basically the same as here, right? As this case too. So we have the substructure length here, then we have this one just to 40, but for our case we can have a maximum of 5. Sorry, where I was. Yeah, maximum of 5. So let me copy this code here. This one is the code for the substructures. Yeah, it's funny, the case 2 is basically similar. Okay. So for case 2, we're actually 83. So this minus, sometimes it will also be -2 for other structures, but for this structure it's -1. So to have case 2, we need to provide the number 3. We remember our position of the structure. We write a placeholder for the length, and at the very end we actually go back to that position and write the calculated length. Okay, and we know that we can maximum have 5 substructures, and for the substructures we actually don't know what they have. Don't know anything about it, so we can use this skeleton saying, okay, for case 2 we write our ID that says we are case 2, we write the length of the substructure or a placeholder for the length. Then for each substructure we have, we write a placeholder for that length, and then the fields for the substructures are coming. How do I know the fields for the substructures? Basically it's just the same. So we go into this method, right? It has a similar setup. We read the tag here, we tag, right? And then we extract the ID, and then we ID -1 is this one, and this one is ID -2, and this one is ID -3. So ID is an EAX. Let's say ID is number 1, right? Then I actually subtract it, which gives me number 0. So I have 0, then this code will be executed. So basically, the first jump will be executed if our ID is 1. And then if our ID is 2, it will be -1, -1 is, then at this point it's only here 0. So it will take this jump if our ID is 2. Or if our ID is 3, it will take this jump. So it looks like there's not a jump table here, but just 3 jumps. So it means our substructure has actually 3, 1, 2, 3. 0, sub 1, sub 2. We have 3 substructures here, and this one, the first one is, this one is case 0, right? And this one is case 1, case 3. Okay, so we can see for our first case here, what are we doing? We're reading an integer. Okay, so write int, say 4 byte. Sorry, 1, 2, 3. This one, this one, this one. So our first case is ID 1, int 32. And for the next case, what's happening is we're jumping somewhere here, and we also read an integer. Okay, and for the last case, okay, basically for all 3 cases in this instance, we just read the int 32. Okay, and that should be our substructure that is nested in case 2. Substructures can also have a jump table, just like the parent structure. So it can be that if I go to this method, you will see an entry just like here with the jump table if it has more cases. So it's a case to case. You need to evaluate what individual cases do and then replicate that. If I go to the graphical view again, so if I look at the next case, this one also looks a bit complicated. I don't know where it goes. I need to check, but then case 2, case 3. For case 4, we can see, okay, it reads an integer, reads another integer, yeah. This one also calls a substructure. Okay. So we can actually see that for the skill yeah, it's quite complicated, I would agree. Some cases may be more simple, like this case, you can see it only reads the short, and that's it. So you really need to evaluate case by case, what are they doing to derive at the value. The other thing is you want to give your function names so you know when they are called instead of just having a offset. So how could you do that? So I would provide these here. So you basically can just copy this one. You press Ctrl+G, you insert this one, and you come to the function. So this function I've already analyzed. It reads an integer. We know this because it operates on 4 bytes. It reads a byte, saves a byte, read, save, read by save, read by save. So it operates on 4 bytes, and that means you're reading an integer, which is 4 bytes. So again, what I did here is I mark the method, I say analysis, and I add it as a method. Then on the first instruction, you press and you press shift and colon, and then you can give this function a name. In this case, you want to name this function like this. The moment you give this function a name, it will pop up in other places like this. So the first thing you want to do is you want to name these 4 functions, at least, to give it the proper name. So that's easier for you to identify it. The other thing is you want to check your return code. So now we are in this method that passes the skill, but what's important is if we look in the call stack, who actually called the parsing skill method is the one before, this one. And this is also the method that checks if I should use a variant or no variant. So if you check, for example, AA is 170, and we can see that the first thing we provided is 153. So there are 2 variables, 170 or 153. And for our case, we check if we are this one. If we are not equal, we will not go there. If we are not equal to AA, if we are not variant, so we are no variant, we go to this. This method here is basically the same as this, but it uses the var_int methods instead of the int32 methods. Yes, so why I'm pointing out this one? So this is a setup you will see very similar. So every time you go one back in the call stack from the method where you found its parsing, this is like the parent method, and it will actually, after I call this method, it will have a test here. It will actually check if there have been any error during this method. Check errors. So what you want to do is the structure you provide, you set a breakpoint here as well. You let it run. So it will go a few more times to the jump table for each of the cases I have. But once it has computed all the data, it will come here and it will have a return code in EAX register. You see it's FFFFE, which is an error code. And the error code, you can look it up here. So it basically say the buffer is too short for the reading. So potentially in my data, I somehow say that you have more data than you actually have. So that's why it gives us this error code. And if we're having an error code at this point after our parsing call, it actually means all the data will be disregarded. So you will not see any effect in the game. So what you need to do is you need to make sure that the structure you craft will not prematurely exit this method and will not have an error like FFFE. So what you want to have it to be all 0, 0, 0, 0, 0. Yeah, that means there was no error. So as long as there's an error, your structure will not be used by the game, and you can. And each read method will return an error code. So you can see that we read value in 23rd here, 32, and then we check the error code, right? We read the integer here, we check the error code. So in case, let's say this integer had an error while reading, we actually don't have enough data to read the full integer, then it will have the error code FFFE, and it will check if I have an error code in my EX. Basically, I check if EX is not 0. And then I will jump here. I will not move an error code in EDX because I already have one from my previous read call. And then I will just return the method while EAX stays in the error. So you can find out which of these methods actually caused the error by checking their return codes. Or basically, you don't necessarily need to check all the return codes. You just make sure that you check that if there's an error here, then that means some of this data is wrong or something is wrong, and then you need to go back to potentially step through this method or you set a breakpoint behind those things, right? I set a breakpoint behind read integer, set a breakpoint behind read short, and then I try to figure out at which instance I actually have the error code. So if I know, okay, this is the error code, then I know, okay, my error is in case 1. I need to look into my case 1 data. Or if the error is here, then I know my error is in case 2, and so on. So just to summarize. So the first thing is, how do I identify where my TLV is being passed? I do that by providing data to a structure that I want to analyze. Structures are most likely identified by a list of bytes. In 99% of the cases, I would say that is a TLV structure, right? So the first thing we need to do is we actually need to feed it some bytes to the structure. So what I did here is that I say, okay, my skill is whatever data I create here in getSkill method, right? So first of things is we need to provide the data. And we know that one of the first things in a TLV structure that's happening is we are reading the var uint. And so what we are doing is in the debugger, we set a breakpoint on read var uint. We set a breakpoint here. Then we execute our code, and if this breakpoint hits, we most likely know that we are in the method that is passing the TLV. We can then either execute to the end of this method and follow the return, or we can look at the call stack, which method has actually called the read TLV value, and then you should end up to something that looks like, you should end up at something that looks like this one, right? You have the read TLV, and then you have the shift that extracts the ID, and then you have a jump table. If you don't have a jump table, the other case can be that it looks like this, right? You have the read var uint, you have to extract the ID, and then you just have a few jumps. You don't need a jump table if there are many jumps. So this is how I know where the TLV is passed. Then the next thing is I can check if the call stack who called my TLV skill method to know when the whole method completed, that I can check for the error code. And then the next thing is inside the TLV method, I need to understand that this one is decreased by 1, so my IDs need to be also taken into account for that. And my ID will be checked to a maximum value. I need to understand how many cases I have. In this case, my highest ID can be 9 and my lowest is always 0. So in this case, it should be running from ID 1 to ID 10, right? So ID 1, and then we should have cases like this till case number 10, because 10 minus 1 is 9, and then we're still in the jump table, right? And then the last thing is, for each case 0, case 1, case 2 in the jump table, you need to understand what the case does. Sometimes you can just press G, and then it's quite easy to see what each case does. Usually I would expect for simple cases it would just have a read int, then you go to the next one, it will say read short, read int, read short, and then that's easy to pass. But unfortunately for this example, case 2 is already a bit more complicated by having a substructure. A substructure can be identified, I would say, by having two read ints, right? You have a read int here and a read int here, and then an unknown call. I would say most of the time it means size of all substructures, size of substructure, pass substructure, and you can verify this also by there should be a jump, there should be a compare to the number of substructures allowed, in this case 5, and then a jump that only goes up between the two reads, right? Because this one, we have provided it, but for each substructure I again need to provide the value. So there will be a smaller inner loop here that reads the size of the substructure, I read the substructure, check if I have read 5 or if I have read enough data. If neither, then again, right? So this is a pattern you can see for substructures. And the other thing is that if I set a breakpoint on the var uint to identify where my substructure is being passed, I need to be careful because other structures might also be passed. So that's why I commented them out. If you don't comment them out, you can also just manually check the data. So you can always say, if you're in the var uint method, let me go inside here just to have a quick demonstration. You can set a breakpoint, I think somewhere here. I think here maybe. Let me try. So at this point, I think EC points to the location of the buffer. So if I follow this one in the dump, you can see here's my buffer. 99 is the var or no var, 7 is the length, and then I have 7 and 11 here, which is probably my first two. So let me check what I've actually, it will be difficult. But it should line up with what I've sent here, right? 7, So this is the buffer of the player init method, and this is the buffer of the skill. It lines up with this one, 0, 7 and 11. So I have not applied the changes here. So I've written some more, but I think I've only written like one case perhaps. Let's just verify. So 7 is this thing. This one is the no variant. It's a byte, and then we have an integer 1, 2, 3, 4. Integer of 7. That is the size, I would say. 1, 2, 3, okay. And then we have written a tag. This tag is only 1 byte. 1, 2, 3, 4, 5, 6, 7. Yeah. So the tag is just 1 byte. And then how do I write the size again? Yeah. I think this is showing outdated data. Let me apply the changes and do it one more time.